Okay, I'm sure everyone gets a pop-up about that. All right, it is my pleasure to introduce Professor Cliff Burgess. Cliff got his Bachelor of Science degree from the University of Waterloo and then his PhD from the University of Texas, Austin, theoretical particle physics. Then a short postdoc at the Institute of Advanced Study at Princeton, and then became faculty at McGill University after that, where he was the James McGill Professor starting in 2003. He's now a professor at McMaster University, Department of Physics and Astronomy, and also an associate faculty member at Perimeter Institute for Theoretical Physics. So Cliff is going to tell us today about surprisingly dark implications of supersymmetric gravity sector. Cliff, please take it away.
Thank you. Thank you for that kind introduction, and also for the invitation to talk. And I wish it could be in person. I had my first in-person talk, I was just saying, on Wednesday, and it was completely nice to be back to in person. So I'm going to share my screen here. Hopefully this will all work. I think that's all right. And as far as questions go, I don't know if you have a protocol, but I'm quite happy for people to just interrupt me, because I think it's best to have the question in the heat of the moment, and people, particularly online, it's easy to disengage, and so the question when you have it is best.
Yeah, absolutely. And if you're okay with that, we can do that, and I'll keep an eye out for people raising their hands as well.
Oh, thank you for doing that. Yeah, because I won't really be able to see the chat or the hand raising, but if you catch that, that'd be great. Thanks. All right, and let me turn the timer on here. Good. Good. So I want to tell you kind of about this is a hard talk to give, because it's really two talks, and so it has there's a danger of it running over. That's why I'm kind of watching the time here, but it's basically, I'm very excited by it, because it's one of these theories that seems like it's smarter than we are, in the sense that you'll see several places you get to a place where it has to fail. You have to be ruled out by some experiment, and then when you look at it more carefully, it turns out the theory solves that problem for you without any new ingredients. So and what the theory does is it describes. I'm going to motivate it coming from high energies. But it describes things, it has implications for the very lowest energies, or for cosmology in particular. And that's kind of remarkable. But because of that, if I don't give you the motivation from high energies, it's just one more crappy model of low energies. And so I need to take you through the motivation, which I hope is not too onerous, because that's normally the part that the theorists would all be into, so and it may not be so interesting to your audience, but I'll try to make it so you don't have to gnaw your arm off to stay awake in that part of it. So let me see if I can advance the slides here. Here we go. So it's work done together with Danielle Deneen, who's a very good undergraduate at McMaster and who's going off to grad school next year to Cambridge. So keep an eye on her. And Fernando Quevedo, who's I was a graduate student with, and we've collaborated for many, many years. And most of what I will talk about, I should ask, can you see my mouse?
We can, yes.
Yeah, okay, I guess that's good. So I'm mostly going to talk about what's in this paper, the yoga dark energy paper. Yoga it's a natural relaxation mechanism. But there's a cluster of ideas here which we've been working on for some time, and are continuing to work on, which I probably won't talk about most of them, but just to give you a sense of this, I'm giving you a slice out of what's a very exciting, to me, picture, and there's a zillion directions to go. And I hope that some of you will be interested enough to join into that. So the point of this paper I'm going to tell you about is, at face value, it's a model of dark energy, and you might say, well, so there's lots of models of dark energy, and there's no way that we're going to be able to do measurements in cosmology that are good enough to distinguish all those models. But as you also know, dark energy has a lot of problems embedding into particle physics, because the things you like in cosmology are the things that high energy physics hates to give you. Things like small masses for scalars, or or small vacuum energies. And so this is kind of, this model is aimed at those problems. And so the hope is that if you can solve those problems, the very rare subset of theories that embeds well into particle physics will be, it'll be easier to distinguish whether that's right than it is to just take random models of dark energy. And so there's three ingredients that this model has, which I'm going to be motivating in great generality. And the theme of them is that they are symmetries, which I'm going to argue are very generic consequences at high energies. And although they arise at high energies, because they're symmetries, they kind of control what happens at low energies, and that's going to be the power of the their explanatory power is coming from that. They are also generic to high energies, and I mean that in a very specific sense. In this earlier paper with Sven Krippendorf, Michele Ciccoli, and Michael Kupke, made this point. These symmetries I'm talking about are not kind of things that you sometimes have. They're really generic. Essentially, I'm going to think of UV physics as being string theory just because it's concrete, and you can ask questions of it that are very focused. But all I'm really trying to use is information that we have at high energies. And I think that there's a seam of information at high energies that we haven't explored yet, surprisingly, coming from these kind of motivations. And the punchline will be, at the very end, I want to make sure I get to the very end, because the implications it has for low energies is a very, very rich dark sector, a supersymmetric dark sector, essentially. That's going to be where the low energy supersymmetry lives, it turns out. But that sector has lots of potential implications for neutrino physics, which I know is of interest in SNOLAB, but it also comes with new mechanisms for hiding some of these new ingredients at low energies from observations in the solar system, for example, tests of general relativity. And the existence of these mechanisms is almost as interesting as everything else, because it broadens your mind as to the kinds of theories I'm going to tell you about are the kinds of theories that I would have said were ruled out a couple of years ago. And it turns out that they're not, in an interesting way. And so it's the main message will be this low energy bonanza that seems to fall out of this motivation. So let me sketch out the way I'd like to make the pitch. So I want to start with this first part, which is the motivation for those symmetries. And there'll be two symmetries. And the mechanism that I'm alluding to here is there's a secret that's buried in the string literature that was discovered in 2004, where they've managed to keep it secret from the rest of us by hiding it in the string literature. And it's basically the statement that these two symmetries together are more powerful than each of them separately. And so I'd like to explain what was going on there, because even if nothing else I'm telling you is right, the existence of this mechanism is kind of interesting. And then I'll tell you about the model itself. And there's two parts to that. I'm going to tell you kind of what we put into the model. So in addition to those symmetries, I'm going to have two ingredients. And this is the part, if anything gets cut in the talk, it'll be this. There's a relaxation mechanism that I will talk about, possibly. And then there's a stabilization. In the end of the day, there's a field in the problem that's going to be very, very large. And all of the hierarchies in nature, the electroweak hierarchy, the hierarchy between the standard model scale and neutrino masses, and the size of the dark energy are all going to be controlled by the value of this field, which is a very large field. And so part of the story will have to be what stabilizes that field. And so there's a way in which the potential for that field is calculated, which is this RG modulus stabilization, which I probably won't go into because it's mostly technical and it's interesting in itself, but it's kind of probably too much for the time available. But then these last two things are what kind of fall out. And so the screening mechanism is where I'll talk about how the upshot will be there's a very light field that's long range in the solar system scales, and it couples with gravitational strength. And so it should already have been ruled out by solar system tests. And it turns out it's not. And it's not because the coupling is weak. It evades the constraints because there's two fields, not just one. And the two fields interact with each other in a way that makes the observable tests for their presence small, even though one of the fields has a coupling which is naively would have ruled it out in the absence of the other. It's kind of an interesting, we call it homeopathy, because it's this other field, as long as it couples just a little bit to matter, doesn't matter almost how much it couples, as long as it's there, changes qualitatively how the answer comes out. And there are some surprises in cosmology that are associated with that same mechanism that will be the main punchline at the end. There's a UV completion story. There's as you'll see, the theory breaks down in some energies, and I'll tell you what the energies are. And if I get to it, we have a picture as to what the completion is. And it turns out to plug into, this is not my first rodeo. There was a time when I gave a talk at Snow Lab about supersymmetric large extra dimensions, and there's an angle here which touches on that. And if anyone asks, I'll say it. I won't say it in the talk otherwise, but this mechanism I'm telling you now is more or less the low energy mechanism of that earlier story, but it also tells you why that earlier story didn't quite work when we did it before. And so it's for me, that's a very satisfying. Okay, so what about the motivation? So I'm talking in the subtitles here about naturalness, symmetries versus swampland, and the picture is meant to show you a sunlit uplands as opposed to swampland, to not prejudice you about which is the better picture. But the story here will be, I want to kind of integrate what I'm describing into what's going on in particle physics now to a certain extent, where people are trying to extract constraints on low energy physics from very high energy physics. And the swampland mechanism is a very popular way of doing that, but I'm going to argue against it a little bit. So the basic story is that we know that nature comes to us with many scales. So if you imagine these ticks all being thresholds in nature, down here is the weak scale, up here is the Planck scale, and for all we know, there's all kinds of scales in between. That seems to be the pattern, that every few decades in energy, there's something new that happens. Now we know that if you know what's going on at high energies, you can predict things at low energies, and there's two kinds of predictions. There's the ones that are very that depend on the details, and there's the ones that are more robust, that just qualitatively are kind of don't depend on the details of what's going on at high energies. And so if you think about QCD as the example of the high energy theory, an example of a UV specific prediction would be to say the value of the proton mass. You really need to kind of take QCD and calculate it in detail to see why the proton mass is what it is. And there's not a general symmetry reason why the proton has the mass that it has. And that's in contrast to the soft pion theorems, where you know that the lowest massive states in QCD are the pions, and their low energy interactions are completely governed by the symmetry breaking pattern that QCD has, the chiral symmetry breaking pattern. And so that distinction between UV sensitive and UV insensitive is a useful one, particularly for what I'm going to be talking about, because many of the problems we have in particle physics are of this nature, which the things we like, if they're UV sensitive, they're difficult to understand at low energies. And so the distinction between them is very useful. Now, the swampland hypothesis, for those who have run into it, is basically the assertion that when people have looked at, say, taking string theory as the example of high energy physics, if you look at kind of what you get, people have been doing it long enough that there's kind of a list of things that are common and things that are uncommon, and they're trying to abstract out of that general lessons for low energies. And so an example along those lines is we seem to be living in a universe which is expanding, but expanding in an accelerated way. And that is very de Sitter-like geometrically. And it seems relatively hard to get that in string theory. Not impossible, but the constructions are a little bit baroque. And so people have tried to abstract these things into statements that because generic field theories allow you to make the universe expand in an accelerated way, but string theory has a harder time, people have made the hypothesis that not all field theories complete to a string theory. And so the ones that don't are not ones we should be talking about, and we should be just focusing on the restricted set of ones that do complete the string theory. And so there's a discussion about which ones do, which ones don't, and so on. But the assertion there basically is that this perceived difficulty in getting expanding accelerated universes is one of these UV informative predictions of low energies. And the spirit of what I'm going to tell you is just the opposite of that. It's that I'm going to argue that these things that people are focusing on are really better thought of as consequences of symmetries. And so in that sense, they're much more like soft pion theorems. There's something which is generic at low energies, but there is information coming from high energies, and that is the symmetries themselves. And so they're approximate and they're accidental at low energies, much like the soft pion theorems were. So I'm not going to pursue that really in the talk, but this spirit of the treating the symmetry, exploring symmetries and learning about classifying the kinds of differences that you get in predictions at low energies from things like string theory is the spirit of what I'm doing. But I'm going to argue for you in practice in this talk that it's very much more informative about low energies than just the statement about de Sitter space. So related to that, since we're talking about low energies, is naturalness issues, and because naturalness issues have a bit of bad press because the LHC wasn't full of supersymmetry. I want to be precise about what kind of naturalness I'm talking about, because there are many kinds, and not all of them are as defensible as others. So naturalness is a quantification of how hard it is, how robust low energy predictions are coming from higher energy theory. And so the observation is that if you have a small thing in your problem, a small parameter in your problem, say you're trying to understand why a nucleus is smaller than an atom or something, then nature has many hierarchies of scale, and we now understand that when we write down a theory, we're not writing down the theory of the world. We're just writing down some effective theory that applies at some scale. And the statement of technical naturalness, which is the one I'm going to use, is that if something's small, you should be able to understand it at any scale you choose to ask the question. So if you're interested in knowing why nuclei are small compared to atoms, you can ask that in the standard model. And there it's because the QCD scale is bigger than the electron mass and the fine structure constant small. You could integrate out the high energy physics and talk about protons and neutrons rather than quarks and gluons. And then there's an answer there. And so the statement that something is small and technically natural is the statement that the small thing is explained to be small at some high energy scale, and then it stays small as you integrate out physics to get down to the low energies where it's measured. And of course, famously, the Higgs mass is not of that form. If at low energies, in the standard model down here, the physical Higgs mass is given by some parameter in the Lagrangian plus corrections. Everything down here, the only scale in this problem is hundreds of GeV, and so all these numbers are hundreds of GeV. But if there were some physics at 10 to 11 GeV and above that scale, we had tried to write down the standard model sector of that theory, there would still be a parameter that would contribute to the Higgs mass. The physical Higgs mass is a physical thing, it doesn't change. But the parameter in the Lagrangian at this higher energy is not the one in the lower energies, because all of the quantum corrections involving these high energy particles that are not in the standard model aren't in the low energy theory, and so they can't appear as quantum corrections. So their contribution gets down into the low energy theory by being rolled into this effective parameter that we have in the standard model that describes the Higgs mass. And so you can calculate the Higgs parameter at low energies in terms of the one at higher energies. And if it's not natural, what happens is that they're not both small. The one at high energies is large, but there's an incredible cancellation that happens between the one at higher energies and the quantum corrections of the explicit particles that are around. And naturalist arguments, you can take them or leave them, but the observation about this kind of naturalness is that we know of many hierarchies in nature, and they're not all in particle physics, they're condensed matter physics, and every single one of them that we understand works like this. And so it's kind of not so radical to ask the hierarchies that we understand to do this. And I say every one we understand, there's a notable one we don't understand at low energies, and that's the elephant in the room. That's the cosmological constant problem. Here I've changed the scale to electron volts. The weak scale is at the top. The cosmological constant scale is down here at 10 to the minus 2 electron volts. And if we just have that same story and we ask about the curvature of the universe in terms of a parameter in the Lagrangian, now the standard model is the problem. If I ask what that parameter is below and above the electron mass, the one below the electron mass is the one we measure, or it's not similar. It's similar in size to the measured vacuum energy, but the one above the electron mass has to cancel the electron contribution, and that cancellation has to be in one part in 36 decimal places. It's kind of an incredibly accurate cancellation. And so one of the things that makes people worry about these naturalist arguments is the cosmological constant problem. The electroweak hierarchy problem is comparatively easy because all the physics above the weak scale, we don't know what it is anyway, so we get to make it up. Here, the problem is at low energies. It emphasizes that the electron is the problem for the cosmological constant. It's not anything that you're going to fix at the Planck scale. One of the ways you can solve the problem above the weak scale is through supersymmetry, and in supersymmetric theories, the cosmological constant, or the vacuum energy, is related to the order parameter for supersymmetry breaking, which I'm going to talk about later on, call it F, has dimensions of mass squared. And it's generically true that the potential energy in supersymmetry is given by the supersymmetry breaking scale to the fourth power. And so when I tell you I'm making progress in the problem, I'm going to give an answer which is smaller than this. And you see that this can help you at scales above the weak scale where we could have supersymmetry be unbroken, but it doesn't help you with the electron because we seem to know that the electron is not supersymmetric at the scales it would have to be to solve this problem. All right, so that's motivation. Took a little bit of time. So what about these symmetries and what's the mechanism and what's the model? So there's two symmetries I want to talk about, and then I'm going to combine them into the mechanism. So I'm asking kind of what's generic coming from high energies that we can use at low energies. And the main one that it's going to be that hasn't been used yet is a scale invariance. That there are it's generic that essentially every string vacuum that's ever been found has scale invariances in it that are accidental and approximate in the sense I will describe in a second. Supersymmetry is also generic, but it's not generic necessarily everywhere. It's generic in the gravity sector, and so in a way that I'll make precise in a second. And then the mechanism I'm going to talk about is that those two things together are actually very informative, more than you might have thought. So what's the symmetry? What's the scaling symmetry? So I'm going to claim that it's a very general property, a very, very general prediction for the low energy world, that if you take the space-time metric and you scale it by a number, not a field, I'm calling it lambda, you scale all your other fields by some power of that same thing, then I'm going to argue that the Lagrangian isn't invariant, but it scales by a different power of that same thing. And it's not really a symmetry because the Lagrangian is not invariant, or the action is not invariant, but it's a symmetry of the classical equations of motion because the stationary points of the action get taken to stationary points when this is true. And it's been known since the 80s that this is a general property of specific string vacua. And more recently, it's been argued that it's always there, essentially, in the string vacuum. And there's a simple reason for it. And the simple reason is that in the end of the day, these theories, the theories like string theory, they have no parameters. And so if you're doing calculating in an approximate way and you're expanding in something, the thing you're always expanding in is really a field. The string coupling constant is the value of a field. And so your action comes to you as a sum over these fields, and any one term in that sum, because it's an expansion, is some monomial for that field. And so now it's kind of a pretty banal observation that if I take those fields and I scale them by some powers of this lambda, any one term in the sum will scale in some specific way, and in particular, the first term will scale in a specific way. And that's the observation. That's all there is to it. And the in practice expansions that people do are the string coupling expansion for weakly coupled string theories. There's the low energy expansion. It's often, people are not actually interested in the string theory. They're interested in the fields at low energies, and so they do a low energy expansion. Those are all examples of fields like this. And so it's not a symmetry, and corrections in these expansions will scale in different but specific ways. And so it's a way of organizing how your low energy theory arises. And so there's a couple examples here, which I just show them just so you know that we did our due diligence, that 11-dimensional supergravity is strongly coupled. There's only one of these, and that's because it's only got a low energy expansion. 10-dimensional theories have two because they're also weakly coupled, and you just go through the exercise and they're all there. Now, why do you care? I'm heading towards applications for the cosmological constant and also to de Sitter space. And the important feature of these kind of scaling symmetries is that they forbid de Sitter space and they forbid cosmological constants. So that means that they can be used to try and suppress it. And so why is that? So supposing I have a potential which scales the way I've been talking about, if you differentiate this with respect to lambda and said this is an identity for all lambda and for all fields, so you can differentiate it, it's still true. If you differentiate with respect to lambda, set lambda equals 1, you derive this identity. And then if you differentiate this identity with respect to the fields, again, you get this identity. And they tell you two different things. This one at the bottom says, if there's any field that vanish, if all the fields vanish, so you're at a scale invariant point, so the fields do not transform under the scaling transformation, then this identity says that has to be a stationary point of your potential. So the scale invariant point is always a minimum, or it's always a saddle point, or it's always a stationary point. And this one says that if you have any stationary point, it doesn't have to be the scale invariant one, just any of them. So if the derivatives vanish, then so does the potential at that point. And that's the interesting thing. It says that the minimum of your potential is always at 0 if you have a scale invariant potential like this. That's why de Sitter space is hard to get, because you do have this kind of a scaling symmetry approximately in string vacua. So I think that's, to me, the swampland is a bit of a red herring, but But what's interesting with this is that, unlike supersymmetry, if you spontaneously break scale invariance, it still makes your potential zero. Nothing here said that the solution you're looking at had to be scale invariant. And so what's going on there is that if you have a solution where the fields are not zero, then different fields, different values of those fields are related to one another by scale transformation. So they all have exactly the same energy. But unlike the Mexican hat, where the minimum was a ring and the maximum was a point that was disjoint from the ring, in this case, the symmetric point, the maximum for the Mexican hat, is now amongst the solutions at the bottom of the potential, because that's just one particular value of the scaling, the zero scaling. And so you're guaranteed that the potential would be flat, even for the places that you've spontaneously broken the symmetry. And so it's not such a remarkable statement that the scale invariant point has a zero potential, because there was no scale in your problem. But the cosmological constant problem is saying that we know that there are scales, particles have masses, so there has to be something that gives them scales, that breaks the scale invariance. But it's still true that the vacuum energy will want to be small when you have this kind of scaling going on. So that's the hopeful fact I'm going to try and build on. And of course, people have been trying to build on that for years. in the 80s, people made models along these lines. And the observation that what made it hard was, of course, these are not symmetries, so quantum corrections break them. And so your nice flat potential gets lifted by quantum corrections. And so then there's a story that people tell where they try and get away with it anyway. And those models were basically killed by Weinberg in the late 80s, where he came up with this no-go theorem, which says that doesn't matter if you break scale invariance, he says. Let's just assume that quantum mechanics is exactly scale invariant. Then he says, well, so it's true that your scale invariant point in this picture of the potential has to be at zero. And if you have solutions that are for which the fields are not zero, they have to be on flat directions that are also at zero. But nothing says you have to have those solutions. So there's nothing in scale invariance itself that forbids you having a potential that is only minimized at the scale invariant point. And so although you're always guaranteed to have a zero potential at the minimum, it's not guaranteed to be solving your problem, because you're also going to have all your masses be zero at the minimum. And so that was more or less the thing that killed this line of research back in the 80s. So what he doesn't say is how big this lifting has to be. And so the thought that's going to drive the rest of the model building is supersymmetry is pretty good at keeping flat directions flat. And so the question will be, can supersymmetry help with the scale invariance? And the answer will be, it actually can. Supersymmetry with scale invariance will be better than scale invariance alone in suppressing the size of vacuum energies. So let me just take you through a supersymmetry story. And again, I'm not expecting you to all be supersymmetry experts here. And so the details of the slides are not important. I'm mostly just showing you that there is a Lagrangian, and to specify it, I have to give you three functions. If I imagine calling my fields in my problem Z or Z, I have to tell you a real function K, which depends on both Z and the complex conjugates, and two holomorphic functions, W and this function FAB, which describe the gauge couplings and the superpotential. So all you need to know for that is that there are these three functions that specify your theory. And once you know those functions, there's an algorithm that tells you everything you need to know. So the kinetic terms for the fields are given in terms of derivatives of this K. Subscripts here mean differentiate with respect to that field. The potential is a calculable in terms of K and W. This combination DW is this thing here. It's again, a subscript means differentiate. So you differentiate the superpotential, and then you differentiate the Kähler function. This K is called the Kähler potential, and you add them together, and so you turn the crank, and you get these things. For later purposes, if you work out what the Einstein term is for general relativity, it turns out it also depends on K. So it doesn't have the standard form where you have no fields in front of the Einstein term. So you have to do a change of variables, which details of which don't matter. But later on, I'm going to do something which draw a consequence from that. And I just want to flag you that it had to be done on the way by here. The important thing for me now is so scale invariance will be some condition on these functions K, W, and F. And the main reason to show you this Lagrangian is it's kind of clear that scale invariance, if I want this to scale, then W and F and e to the minus K over 3 are the things that have to scale. And that's the naive thing is just true. And so that's the point of showing you this Lagrangian. Now, there's a nice thing that happens if K in particular scales. And so there's a thing that was discovered in the 80s called a no-scale model. If K satisfied an identity, that this combination of derivatives, this thing with a superscript is if I have two derivatives in a subscript, that's two derivatives of K. and that's a metric. And so you think of it as a matrix, and this is the inverse matrix to that. So you build this thing, and if it's equal to 3 in Planck units, that was called a no-scale model. And the reason it was interesting was, if you go back to that expression for the potential, if you had fields that did not appear in the superpotential, then there's this common factor that appears, which is 0 when this identity is true. And so people made the observation that, boy, those are nice theories, because the potential energy is 0 for them, even though supersymmetry breaks. It turns out that supersymmetry breaking is controlled by the value of this combination dW. And as long as W is not 0, then this combination is not 0. So you've got non-supersymmetric solutions which have 0 potential. It was the observation that made in the 80s. And somewhat later, people observed that if you had scale invariance, so if your fields all scale in this particular way, they all scale with the same power, and if e to the minus k over 3 scales with that same power as well, then a consequence of that is this identity. So a sufficient condition for these flat potentials is scale invariance, and that's not so surprising, because we know that scale invariance should make potentials flat. Now, the interesting thing is that they didn't know then, but which we now know, is that scale invariance is sufficient, but it's not necessary for these no-scale models to have flat potentials. So it turns out that there's many categories of these flat potentials in supergravity. This A is the most general one. It's people in the 80s identified the necessary and sufficient conditions for flatness. But I'm going to focus on this category C and D, which are subsets. So category C is the one I described. It's the one where K satisfies this identity. So these are because these are in a subset of A, they have flat potentials. And the scale invariant ones are a subset of these ones. So this example that I've written here is an example which is not scale invariant. This F is an arbitrary function of some other fields. So when I scale all the fields, this first term scales the right way to be a no scale, to imply flatness of the potential, but this one doesn't. So this is just showing you that there are examples in category C that are not in category D. And why do you care? The reason you care is the whole story about using these scaling symmetries is how big the corrections want to lift the flat directions. How big are those corrections? And everybody expects that as soon as you put in quantum corrections, you're going to break these symmetries because they're not symmetries. And here's the magic that happens, is that you can start off with a scale invariant theory where you're in category D, and then it is true that the quantum corrections will break the symmetry. But what happens is that they leave you in category C, so your potential is still flat. And it's only when you go further down the expansion and these corrections that break the symmetry that you start to see that the potential is not flat anymore. And so the punchline here is that supersymmetry together with scale invariance can make your potentials flatter than they might otherwise have been. And that's the thought on which the model is going to be built. So let me give you a concrete example of how that works. Let's say there's one field, it's a big field, and I'm imagining that the theory comes as a series and 1 over that field. In the example I'm going to show you, that field has a VEV which is 10 to the 30, so it's a really good series, a really good expansion. Now, and we're imagining that we have the scale invariance, and it's there because the scale phi, and because it's a series in phi, each term scales in a specific way. So it's a special case of the story I told you. So this first thing is scale invariant, and as I've argued for you, it's a no-scale model, because if I just differentiate K defined in this way with respect to phi and phi star, it satisfies that identity. So it'll have a flat potential in particular, as long as phi is not in the superpotential. Now we do the corrections. The next correction will be down by 1 over phi, so that'll be this. A0 and A1 are just some coefficients depending on other things. Now, this is not scale invariant, but I showed you as the example before that this is still a no-scale model, so its potential is still flat. And now if I go to the next order, I get a term which is now no longer a flat potential. And so at this point, I will start to see that my potential's got some shape to it, but it's smaller in powers of 1 over phi than the naive thing. And because phi is so large, I'm going to argue that 1 extra power of 1 over phi is good enough to describe what we see in cosmology, at least part of it. And then this slide is just to argue that string theorists found this by concrete examples. They just had this happen. They looked for a correction and they were surprised it wasn't there. And then they kind of reverse engineered to see why that surprise happened. Okay. Now you might say, very nice, it's all supersymmetric, but supersymmetry isn't true. It hasn't been seen in the LHC. So here's the second symmetry story. if you have a supersymmetric theory, multiplets get split, and they get split by an amount which is proportional to their strength, the strength of their coupling to the supersymmetry breaking order parameter. So the weakest coupled thing is split by the least, and that's typically gravity. So the splitting in the gravity sector is normally less than in the other sector, call it the standard model sector. So if we only can see up to here, we would see a very non-supersymmetric particle world coupled to a very supersymmetric gravity world. And the next few slides I'm going to skip because I can see that my time is getting low. But the upshot of them is that this observation, which had been made also back in the 80s, wasn't very useful because no one knew how to write down what that theory looked like, because you're coupling supergravity to non-supersymmetric matter. And that problem was solved in the last 10 years, it turns out. And there's a story there, most of which doesn't really matter much. And what I'm going to make the one observation that what does matter is that, let me get to the bottom here, is that the fact that gravity is supersymmetric, the reason that's important is that it makes the scalar potential have this very specific kind of sum of squares form that we had that I showed you before. And there's a deep reason for that, which is coming from the supersymmetry in the gravity sector. And that's going to be important in the model that I actually write down for you later on. So what is that model? So the idea is to take the scale invariance, to take the supersymmetry, and to take the standard model not being supersymmetric and just see what it looks like at low energies. And in particular, hope that we can choose this large field to be able to explain the hierarchies in nature that we see. So I'm going to need that field. I'm going to call it T instead of phi. It's actually a complex field, and so there's a real part, which is the field that we're going to expand in. It has an axionic partner, it turns out. These are all built in by supersymmetry, and there's a fermionic partner as well. These are very light. These are in the gravity sector, so they're supersymmetric. And I'm going to ask that everything be in a series in powers of tau. And so I just have to follow my nose now. So I take the supergravity rules and I build in that it's a series in tau. I do exactly what I told you, where I called it phi, and now I'm calling it tau. It starts off with tau, then there's something independent of tau, there's something going like 1 over tau. And then these things, this little k and little h, are just arbitrary functions of everybody else. Y here is a standard model field in the rules that I didn't tell you about. And we turn the crank, see what we get. And the first thing is, this W doesn't depend on tau, and that's because there's a symmetry where the scalar, the A, shifts, and so it's forbidden by a symmetry. So the things I'm not writing down here, I'm not doing it because it's not a choice. I'm not giving you a bespoke an answer. This is just the symmetries are driving the choices I'm making here. Now, one thing is this thing. Because this superpotential doesn't depend on tau, that means that all standard model particle masses are going to depend on tau in a very specific way, it turns out. And that's because of the story about the Einstein, the general relativity action having this e to the minus k over 3 in it. When you actually go to the, if you actually ask what's the mass of a particle in Planck units, it turns out that there's a universal expression for what all standard model masses will be. And they're given by e to the k over 6, which, because tau is very large, is basically 1 over root tau. So every single particle in the standard model, except neutrinos, because in the standard model they would have been massless, are going to have a mass proportional to 1 over root tau. Now neutrinos, basically what's happening is that the tau dependence is coming through a scaling. So everything that has dimensions in the standard model, that's just the Higgs value, will be proportional to 1 over tau. Now the neutrinos get a mass which is quadratic in the Higgs field, so they get a mass which goes like 1 over tau. And so, given that neutrino masses go like 1 over tau and standard model masses go like 1 over root tau, we can figure out what the scale m tilde is and how big tau is. So m tilde has to be the Planck scale, it turns out, and tau has to be 10 to the 30. That gives you an electron volt for the neutrino masses, and it gives you the weak scale for the standard model masses. And now, given that, so tau will be setting those hierarchies, and then now I want to make an argument for you that the potential has the right size at its minimum as well. Before I get, this is just what I told you about the numbers. Along the way, if we talked about the potential, I said that these k's and h don't depend on tau. They can depend logarithmically on tau, but that won't matter for what I'm going to say. There's an issue that you have to worry about, that supersymmetry is badly broken, and I have to check that, and so I will check that. And so now I want to, this is going to, these slides look complicated, but all you have to do here is track the tau dependence of the size of the potential. And these formulas, I'm going to tell you what that is in a cleaner way than it looks. And the formula is this there to show you that we did the work, and I'm not just making this up. So you just turn the crank, you get the potential that you get. It comes to as a series in 1 over tau by construction. Now the big term is the first one. It's of order 1 over tau squared. That's the thing that is the supersymmetry breaking scale that you'd normally expect it to see. The correction goes like 1 over tau cubed. And then the next term goes like 1 over tau to the 4th. It turns out when you put the Planck masses in, each of those taus comes with another Planck mass. Now, here's the point. Because the big term is positive, it's a square, I can imagine there's a field, as long as there's a field in there that for which that coefficient goes through 0, this field will always be minimized where this thing is equal to 0. And that's the relaxation field. So let's imagine we have a field that does that. It's Wx depends on phi in such a way that it passes through 0. I minimize phi. I'm going to kill that term off if all I had was that first term, but really I also have these other terms. So what really happens is that Wx doesn't go to 0. It goes to something which is Planck suppressed and down by 1 over tau. And once I go to that minimum, at that minimum, everybody is the same size. They're all the size of this last term. And this last term is of order 1 over tau to the 4th, which is of order the weak scale to the 8th power, because the weak scale goes like 1 over tau square root. And so this gives you something which is of the size of the m weak squared over m Planck quantity to the 4th. That's numerically the right size to be the vacuum energy in cosmology. And then let me just leave it at that. And then the bottom line summarizing is this field tau has a kinetic energy. Standard model masses go like 1 over root tau. Neutrino masses go like 1 over tau. And the story I just told you tells you that the potential goes like 1 over tau to the 4th. And that value, that same value for tau accounts for all of those hierarchies, the cosmological constant, the neutrino masses, and the standard model scale. You can kind of see that the neutrino masses and this cosmological constant are similar in size because they both go like 1 over tau. There's a story about supersymmetry, which I won't get into. And so the main point is that I told you I was going to get a suppression, and this is the suppression compared to the supersymmetry breaking scale. So that, and because tau is enormous, it's 10 to the 30, this is an enormous suppression, much, much better than any other theory you've ever seen predicting for the cosmological constant in a natural way. So I want to close in the last 10 minutes with the falling out part. So that's all very nice. I claim that there's that low energy is a nice thing was going to happen. So I want to get to that nice thing that's going to happen. And there's two things here. One is that tau field. It's so light. It's going to turn out to be. I skipped over it, but it's the Hubble scale in mass, 10 to the minus 32 electron volts. Very long range force, and it couples in a very specific way because every mass in the problem goes like 1 over root tau. Turns out that coupling is way too strong to survive to pass solar system tests. But the theory is going to not be ruled out anyway. So I want to explain that. So the theory we're talking about at low energies is, this is the kinetic energy that I told you about. I didn't write it explicitly before, but here's the tau field. Here's the imaginary part of the same field, the axion. Here's that potential I argued for you was there. And this is the standard model part. And all you need to know about the standard model part is that all the masses in here go like 1 over root tau. And what we want to do is just look, what's this look like in the solar system? These are the masses I told you before. I guess I'm telling you this just there's other fermions around. I should say in passing, the gravitino has a mass which is similar to the neutrino masses. If you're interested in neutrinos, that would be useful to know. The dilaton mass I told you is very light, and there's a good reason for it, which I'll skip. But the main point that's dangerous about this field tau is that it's a field which is very, very light, Hubble scale in mass, but it's coupling. It couples in what's called a Brans-Dicke way. And the Brans-Dicke was a scalar theory that was invented in the 60s as an alternative to gravity. And it has a coupling constant in it, G, which in this theory turns out to be 1 over root 6. And the Brans-Dicke theories are known to be inconsistent with solar system tests unless G squared is less than 10 to the minus 5. So normally you get to this point and you say, well, that theory didn't work out. And so now we have to do something else. And I want to argue for you that actually this prediction, this theory survives, even though it looks like it shouldn't be surviving. There's a story about the axion, which I will skip for want of time. So the thing that kills the theory is tests like the Cassini bound, the light signals as they pass from Saturn, from the Cassini probe to the sun, past the sun to the Earth, they slow down because of general relativity as they go by in the gravitational field. And the success of that prediction, general relativity prediction, tells you that the scalar tensor theory, the presence of the scalar field that's so light should have been ruled out, because that test, the agreement with the Cassini bound, says that that coupling, which was 1/√6, should have been less than 10 to the minus 5. And the problem is that this prediction that I'm telling you here, 1 minus gamma, is actually incorrect for this theory if you're careful about it. What really happens is that this dangerous field tau, which couples to matter, it interacts with this other field, which is also massless, this axion field A, in a way, so they interact with one another at the derivative level. And what happens in life is that the matter couples to tau. It likes to want to set up a tau field, but these interactions between tau and axion turn them into axions. So what you really do is set up an axion field, but then test particles don't couple to the axion, so they don't see it. And so the presence of the axion is the thing that allows you to get away with the coupling of tau to matter, even though that coupling is too large. So there's some details of that, which I'll skip. But I want to really drive home that this is a system you can just solve. So if I solve the field equations for these fields, this is what the solution is for a spherically symmetric source. A, B, C, and D are integration constants. X is this particular function of 1 over constant plus constant over R. And this is the general solution for these two fields outside of a spherical source. It happens to satisfy this identity, which is saying that these things live in a circle. And so if you now ask what those integration constants are, they're fixed by the value of the fields at infinity, and they're also fixed by the boundary condition with the surface of the star, or whatever it is that this is the source of matter. Rho here is the energy density of the what's in whatever in the matter, and curly A is the axion coupling, the source, the analog of the energy density for the axion coupling in that matter. And so C and A are given by the coupling to matter, and B and D are given by the fields at infinity. I'm going to give you the answer as a function of epsilon. I'm going to make the assumption that this axion source is just proportional to the matter source. It just depends on the density of baryons, let's say, with some proportionality epsilon, which is a number I get to dial. And if it's 0, that will be the case where the axion isn't there. And then we know that's Brand-Sticky theory, and it's ruled out. Now, here's the prediction that you get in this theory, and you see that it depends on epsilon. As epsilon goes to 0, this thing that had to be small is small, and the falling of the moon and the Earth towards the sun also gives you a constraint on a different combination of parameters. The fact that they're falling the same way towards the sun says that this combination of parameters is less than 10 to the minus 4. And all of these things can be satisfied by making epsilon small enough. There's no restriction on that. The prediction that you would have had for a Brand-Sticky theory is obtained by taking D to infinity and B to infinity with epsilon equal inversely proportional to B with a proportionality constant, which would have been the Brand-Sticky coupling. And these formulas go over to the standard ones in Brand-Sticky theory in that limit. But these show you that that you get away with it because the axion, the field converts to axions rather than to dilitons, and then test particles that that you're actually getting the bound from evade the bound. In the last 3 minutes, let me ask how this looks in cosmology. So the remarkable thing there was that a field with a coupling that's too large, it should have been ruled out in the solar system, now survives those tests. If I just add to it another field, which has also got a very low mass and couples by a very feeble amount to matter, and I don't change the coupling between matter and the first field at all. That's the surprise. The interactions amongst those two fields are sufficient to evade the solar system tests. In cosmology, there's a very similar story. I just show you the equations here just to point out some features of them. You have the Friedmann equation that says that the expansion of the universe is controlled by the energy density in it. There's an axion story where this is telling you how the axion rolls. There's a dilaton story where this is telling you how the dilaton rolls, where chi is the log of tau, what I was talking about before. The potential is what it was before, and the story about how the axions couple to matter is as it was before. And I'm going to show you some plots as to what this looks like as a cosmology to show you that this theory, again, would not have worked because the coupling of the tau to matter is too large without the axion, but the axion, again, saves you. So the tau couples to matter like a Browns-Dickey scalar, like I said before. The potential is there, and then the axion is there, and the axion couples both to tau and to matter in a very specific way. So here's a plot. So here's the potential. This is chi, the log of tau. We have a potential, which I didn't tell you how I did it, but there's a potential which has a minimum. It's an exponential potential 1 over tau to the 4th, which is exponential for chi, which is a log of tau, with a little bit of a divot in it that gives you a minimum. And if you look at the history of the universe, this is the energy density in various fields, and this across the bottom is the size of the universe, the scale factor. This vertical line is now. Radiation is falling like 1 over the size of the universe to the 4th power. Matter falls like 1 over the size of the universe cubed. And the scalar field, if all we had was the dilaton, and if we made the coupling very, very small, which is not what the theory predicts, but if we satisfied the solar system bound, the naive one, you can make cosmologies that work fine. And what happens is that the scalar field has a lot of kinetic energy, but not as much as the other things do back in the early days. And then Hubble friction basically sucks that away, and then it just sits at the bottom of its potential, and it becomes a cosmological constant at late times. And that would be a viable cosmology. Now, when you make the coupling, the one that was predicted by this model, 1 over root 6, you get something like this. So what happens is in that case, it's not a viable model because, again, the radiation falls, the matter falls, the kinetic energy falls, but it never gets to the point where you're dominated by the potential energy. And the reason for that is that the scalar field couples to matter too strongly. And there's more matter around than there is dark energy in the early days. So the coupling to the matter wins. And it pushes you out to large values of the dilaton. It pushes you past the minimum. And then by the time the matter goes away, you're out here and you just keep on rolling. And so you never get to a place that looks like the universe that we see where dark energy dominates. But now the axion saves you. And the axion saves you because of a slide I skipped back here. The axion appears in the dilaton evolution like a contribution to its potential, and it fights the other things. And it's because of the same mechanism that worked in the solar system. And so what happens now is radiation falls, matter falls. The green line is the total energy of the dilaton again. Then this orange line is the potential energy. Oh, and my time is up. Let me just turn that off. Figure out how to turn it off here. There we go. Good. So I'm almost at my last slide here. The axion is this other line here. It's basically tracking what the dilaton does until radiation matter crossover, and then the axion starts to follow the dark matter basically, and it kind of keeps on following like 1 over a cubed. And in the meantime, its presence allows the dilaton to get trapped at the minimum, and then it just sits there, and so then it becomes the cosmological constant we see at late times. And so again, the axion is surprisingly saving the cosmology of this theory to make it something which actually is viable. And there's an even more, and it's even better than that because this is showing you the abundance of things that now as opposed to earlier in the universe. And what the main thing to notice here is that the dark matter is only 18% of what's out there. The axion is 8% of what's out there. Together, they make 26%. That's the dark matter that we would normally say. That's the stuff that's going like 1 over a cubed. So there's a significant component to the dark matter, which is axions in this picture. And the value of the dilaton field makes an excursion very robustly because at radiation matter crossover, the dynamics of it changes. And so it likes to make an excursion. And the significance of that is that means that particle masses, even if they were the same as they are now back at nucleosynthesis, they could be different at recombination when the microwave background forms. And that means that there's observable signals you should expect to see to do with the electron mass, for example, being different at the time where light is decoupling from the early universe. And so the most amazing surprise to me was that doesn't rule you out. That actually can improve your fit to cosmology. There's a famous problem in cosmology that the Hubble tension, the Hubble scale measured in the microwave background is different from the Hubble scale measured nearby us in the universe. It turns out that a solution to that it was identified several years ago was if you were to change the electron mass by about 8% at the recombination and change the baryon density by the same amount and change the dark matter density by the same amount, then you would change the time when the microwave background is formed, essentially, and that changes the distance scale in a way which makes you recalibrate the size of the universe. It gives you a different value for the Hubble parameter, which is about 1.5 times bigger than the change in the electron mass. And that actually allows you to resolve this difference in the Hubble scales consistent without screwing up what you see in the CMB. It's kind of remarkable. But they never knew when they said, well, you can do all those things, but why would it be true that these things would all be the same? And why should it be true that, and if you do this at recombination, why didn't it happen at nucleosynthesis when it would be ruled out? And the theory I just gave you does this for free. This condition is this condition that every mass in your problem scales the same way. So if tau changes by 10%, the electron mass and the nucleon mass and the dark matter mass, they all scale the same way. And that's kind of why this thing is true. And the reason that nucleosynthesis is not a problem is back here, the mass is exactly the same as it is now. It's only changing at recombination. So there's a dynamical way in which these things all happen. And so there's a story here that we've only started to explore, but it's kind of remarkable that bounds get evaded and remarkable surprises happen that the theory was not designed to do these things. I'm going to close with some comments on neutrinos because I think that's probably of most interest at Snow Lab, in addition to dark matter. And so I told you already the story of, there's a very general reason why tau is treating neutrinos differently than standard model particles. But a thing I skipped over was that there's a whole bunch of fermions that are in the gravity sector, which are sterile, and they're all roughly the same mass as neutrinos. So there's a lot of rich structure in which you could find oscillatory physics. And unlike most of the theories that predict light sterile particles, this tells you why they're light. They're light because they're tied to the graviton by supersymmetry, and the graviton is massless. And so there's a very rich structure that is certainly, I would say, if you have models you want to build aimed at neutrino phenomenology, this is a very, very well-motivated class of models, which is not arbitrarily tweakable because of the structure of the supersymmetry in the dark sector. It has the same spirit as the extra-dimensional based models, if you remember those, of neutrinos back in the day. So I'm going to just go to the conclusions guide. So I'm going to skip the UV completions. 3 points I'd like to leave you with. So surprisingly, the properties of physics at the highest scales can be predictive at the lowest scales, and it's these naturalness issues and the symmetries that are addressing the naturalness issues that are the informative thing. I think the swampland approach is interesting, but probably misguided. It's really the robust symmetry consequences that I think are likely to be informative. There's remarkably rich physics that comes out of these symmetries that I described to you at low energies. In cosmology, there's light scalar fields, which as a particle physicist, I would have thought were impossible. There's light fermionic fields, which for neutrino physicists are a playground that is worth exploring. And there's much to check. There's, if this is really what's going on, it's enormously predictive, and it may be ruled out. I haven't looked at large scale structure. If you're changing masses at a time when you can actually see the microwave background and you see galaxies forming, there's almost certainly going to be signals there. And when I showed you that the excursion in the dilaton field and all masses are changing, it settles down to the minimum, but it oscillates for a while. Those oscillations better slow down when stars start to form, because otherwise spectral lines are going to start looking funny. And so there's a whole bunch of phenomenology that is worth exploring, and may also contain surprises like the ones I showed you, such as evading bounds in the solar system and possibly making progress on the Hubble problem. Sorry to run over a little bit there, and I hope it wasn't as theory heavy as I fear it might be. But thank you for your time.
Thanks, Cliff. Thank you for a very nice talk. I see one question from Chris. Go ahead.
Yeah. Thanks, Cliff.
Okay.
Yeah. So your theory, you said that there's kind of a natural scale for the neutrino mass. How wide a parameter space is there? Like, if you're right, what is the kind of possible range that we ought to be looking for absolute neutrino mass, say?
Well, so there's all I showed you was the tau dependence. And so that's kind of the gross hierarchy. And there could be dimensionless factors. Like so in the standard model, I said they're all going like 1 over root tau, but really that's anywhere from the electron to the top quark, right? So there's those dimensionless factors you get to play with a little bit, and those will also be there in the neutrino sector, just like they would have been in a seesaw kind of a model where you have, if someone had just written down a dimension 5 interaction, you would have had the Yukawa structure there, which would still be there. But there's, in addition to that, there's another layer of complication because I skipped the ultraviolet completion story. But that's important for the question you asked. And so what happened in the ultraviolet completion story was, if we had looked at the axion, its decay constant turns out to be similar to the neutrino mass. And so it's basically an electron volt or so. And so, so normally, if you get to an energy where when you're at the energies of the axion decay constant, something has to happen, typically. And in this case, I think I know what happens. And what happens is that you go over to a supersymmetric large dimensions theory, because the electron volt scale is where that would start. That would naturally want to start. And the scales that I told you would actually also make sense there. Having the gravitino mass be that size would make sense because it would just be at the Kaluza-Klein size. That's what you'd expect it to be in that kind of a picture. And so the reason that's relevant for your question is that everything I've told you in this talk was happening at the lowest energies of 4 dimensions. But now, once you get to the electrovolt scale, which is where the neutrinos are, you now have Kaluza-Klein towers of everybody, of all these sterile fields, typically, because the gravity sector is going to now become an extra dimensional sector, whereas the particle physics sector will have to be localized on some brain or something, and so it'll be 4 dimensional. And so that means that there's the richness of the things you can look for. The mass range is essentially going to be somewhere in the ballpark of electron volts, possibly a little bit less suppressed by Yukawa couplings, but then going right up to the weak scale with Kaluza-Klein towers of things. So there's an enormous richness of mixing phenomena, and we've explored some of them back in the day when we were looking at extra-dimensional models. And it sounds like, why, if you have that much richness, why haven't you seen it already? And it turns out that it's not as easy to see as you might have thought. It's those kind of models can exist, but they have many ways in which you can search for signals.
Okay. Thanks.
Any other questions for Cliff? Yvonne, go ahead.
Sorry. Okay.
Hi.
So hi, Cliff. Sorry, I can't put my video. So a couple of questions. So what happened? I mean, I think I missed this field phi. Where is it, and what was it? The phi field that you need to, the relaxant.
Yeah. So there is that field. I didn't talk much about it. Yeah. Well, what would you like to know about it?
Yeah, where is it? Where did it? Because at the end you mentioned everything about the dilaton and the axion partner of the dilaton. Yes. What happened to the phi field?
What happened to that one? Yeah. So that one can be heavier. So that one has to be light enough that it's lighter than all the standard model particles, because it's designed. The thing that it's removing is the standard model contribution to the vacuum energy, which would have gone like 1 over tau squared, because the masses go like 1 over square root of tau. So m to the 4th goes like 1 over tau squared. So that field is what took those out. And so it has to be lighter than the electron in order to take the electron contribution out. That's kind of why you're solving the cosmological constant problem. Or, if this solves it, that's how you would solve it, essentially. And so it has to be lightish, but it doesn't have to be much lighter than the electron. And so it doesn't have to be light enough to be relevant for cosmology or for any of these other things that are going on. And kind of, if you ask kind of what another thing you could ask is there a motivation for it from these higher dimensional from these ultraviolet theories? And there is. That field, if you think about it, that's a field that's been designed for some values of it. For some values, it gives you a big positive energy, because that was the v squared. The first term was positive; it was a square. And then for other values, it gives you almost 0 for the energy, a very small amount. If you in the history of the universe, if you rolled from the first place to the second place and you did it slowly, that would be inflation. So one way to think about this relaxation field is that it's the inflaton. It's a thing that's being designed to interpolate between a region of high energy and a region of low energy. And the dynamics of how that happens is something which we haven't explored in detail in that yoga paper, but we have since explored. I don't know if you would have seen we re-examined some of the string inflation models using the stabilization mechanism that I didn't talk about in this talk. and they basically go through and they solve some of the problems that those models had as well, such as the eta problem goes away, it turns out.
And the other question was, so, well, you also didn't mention much of this, but you have a nilpotent superfield, the X field, right?
Yes.
So you eliminate the scalar, but at some scale, this is going, I mean, linear supersymmetry is going to be recovered. So, but you don't care about that at the moment. How do you know where is linear supersymmetry?
So when you say it's going to be recovered, what you mean is that if I've made this, if I've got rid of the potential energy, I've turned off the supersymmetry breaking, it looks like, right?
Yeah,
and so,
exactly.
That's a great question. So this is the reason why this model wasn't written down 30 years ago. Is that if global supersymmetry was right, what you're saying would be exactly true, because that first term would have been the supersymmetry breaking order parameter, and we've made it 0, so now we no longer have broken supersymmetry. But because we've coupled to gravity, there's 2 reasons why that's not what happens. So the first reason is that Wx doesn't turn out to be 0; it turns out to be Planck suppressed. So it's not 0. And the second thing is, what was the second thing? And the other thing is that the Wx is also not the order parameter. The order parameter is the Kähler covariant derivative. So it's Wx plus another term involving, that's also Planck suppressed. So the thing you have to ask is that combination, that order parameter is a UV scale still. So you have to make it bigger than the weak scale. But you can, consistent with the having minimized, had made Wx smaller than it wanted to be, because smaller than it wanted to be just meant Planck suppressed. It didn't have to be 0.
Okay. Yeah, I'm just imagining that if because the nilpotency condition is eliminating the scalar partner of the
Yes.
superfield, but at some
Right.
energy, the scalar is going to reappear. So.
Well, that's the thing, is that the dangerous thing would be if you allowed supersymmetry to break by too small, then all the superpartners that you got rid of are going to come back down, and they're going to be in your low energy theory. And we checked that does not happen. And the reason is what I said, is that it's Planck suppressed, but it's not below the cutoff.
Right. Okay. Yeah. Thank you.
So it's a counterintuitive place to be. That's why people, I think, missed it.
Yeah. Okay. Thank you. Thanks.
Thanks for the question.
All right. Thank you again, Cliff. I think we're a bit over time, so we'll probably end.
Yeah. Sorry about that.
No worries. No worries at all.
I got to tweak this. I think I can see.
But thanks again for a great talk. And I will probably ask you for your slides, if that's okay, a bit later.
Yes, I can send those to you.
Okay.
Definitely. I have to prune them a little bit because I'm not a sophisticated